The talk that we're going to be giving today is going to very much build on the two previous talks that have been happening in the past 2 weeks, with Jarg and Mark talking about the seismicity and some of the contexts of the earthquakes that have happened in the Canterbury region, and then complementing some of the information that you'll have gotten last week from Mishko, looking at some of the flatland damage that we've observed. We're going to be moving on now towards the hills, the Port Hills. There are some types of behaviors that are quite distinct from the type of stuff that we've been seeing in the flatlands. And we've broken the talk up into 2 parts. I'm going to start by setting up some of the technical aspects of what it is that we've been observing, what some of the causes are for what we've been observing, and giving you some of the context for understanding some of the very specific examples that DHB is going to go into a little bit more detail about. I'm also going to be giving you a little bit of information contrasting the type of behavior that we saw in September versus the type of behavior that we saw in February. So first off, in February, most of the damage that we had that was of a geotechnical nature was only in the flatlands. So it was mostly the liquefaction that we saw and the fault rupture that we had out in the Canterbury Plains that Mark talked a lot about and Mishko also talked a lot about. There was also some limited damage to the Port Hills. This is a picture of some of the damage that we observed on Castle Rock. So there was some material at the top of Castle Rock that came down, and then this lower figure is showing some of the material down in the bottom of the valley near the portal to the Littleton tunnel. Some of this damage was actually quite limited. I remember driving along the Summit Road one of the days after the September earthquake, and we saw a little bit of rockfall coming down off the road cuts right adjacent to the road. Very small amounts of material that came down, and only in limited locations. Contrasting that with what we started seeing after the February earthquake, and then as well after the April 16th and June 13th earthquake, we saw again the recurrence of this flatland damage. But in addition to that, we saw some very severe widespread damage in the Port Hills. We saw things like rock falls, collapse of the sea-cut cliffs, cliff renting, landslides, fissuring, and damaged retaining walls. Some of this behavior was quite new to us, especially some of the cliff renting and fissuring behavior, and we're actually going to talk about some of that in a little bit of detail. So this is an example of some of the damage that we saw post-February. This is the source of the rockfall above the house in Rapaki. You may remember from the media there was a house where a very large boulder came through. This is the source area up here on the top of this hill. Here with some of the material trailing down the hill, you can see the size of some of the blocks, and those blocks went all the way down to the road, past the road, and into some of the houses. And this is an example, one of the very familiar images that we've all seen this is of red cliffs, and this is one of the collapses of the sea-cut cliffs. This is a very severe type of failure that occurred. Some of the other type of failures, not quite as dramatic looking, but also has large implications for the people who are affected by them, is the retaining wall damage that we saw in some of the hill suburbs. This is a retaining wall in Littleton, and over on the right, the arrow there is showing that there was some rotation of this retaining wall here, and that led to deformation of the backfill behind it, and that created a large crack in the road, making that road pretty much impassable. So there were some impacts on infrastructure as well as houses arising from the deformation of some of these retaining walls. This is a slightly more dramatic failure of retaining wall. This is Sumner Road, again in Littleton, and this is a retaining wall here, one of the older stacked rock retaining walls. And you can see that the cracks have gone very much into the road, and a large portion of the road has actually come down. So this is a slightly more dramatic failure with implications for the people who live on that road. So taking a step back, looking at some of the technical aspects of some of the damage that we saw, in order for that damage to occur, there are triggers, and those triggers in this case were seismic triggers arising from the earthquakes. And seismic loads around the world have been shown to induce shear stresses, and shear stresses are stresses in which the material wants to move in a parallel fashion. And these shear stresses on the soil and on the rock will tend to weaken the material that's making up the slope, whether it's soil or rock. And this can lead to the development either of new landslides or the reactivation of old landslides. So material that's just borderline stable might reactivate and continue to move. In many cases, however, completely new landslides are developed in areas where no instability has ever been identified. And in the Port Hills, this is very much the case. In addition to some of these shear stresses, the actual shaking and ground acceleration of the soil and the rock will initiate movement of that material, and this will lead to rock falls, the cliff collapse, the cliff renting. I'll go a little bit more into detail about that in a minute. So we have the trigger, we have the earthquake, which is the setting forward of the motion of the ground. In terms of the seismicity, as we've learned with Mark and Jarg earlier, there are different characteristics to different types of earthquakes. And each of the characteristics of those earthquakes, as well as the characteristics of the material and the topography that we're dealing with, will have implications for how that material is going to behave and what sorts of failure we're going to see. So we've discussed in previous lectures points about the magnitude and the shaking intensity that we saw in the earthquakes here. In addition, we discussed the distance of the earthquake and the depth of the rupture. And this little cross-section here nicely shows the location of the Port Hills and the location of the fault with the epicenter right below the Port Hills, and the direction of the movement of that seismic energy upwards towards the Port Hills right there. And so pretty much they were in a direct line for that seismic energy. In addition, the material that makes up the Port Hills, there's all sorts of different types of materials, and each of those will have a different type of response to the seismicity. And finally, the topography, the shape of the topography and the fact that there is topography to begin with will have implications for the stability. So starting first off with magnitude and shaking intensity. Typically around the world, what researchers have found is that you need about a magnitude of 4.0 to get land moving. And so we had 2 earthquakes now, 7.1 and 6.3, and all of the ones succeeding that. And they're above 4.0, and so they are above that sort of minimum threshold for land to start moving. On top of simple magnitude, there's the shaking intensity, and that shaking intensity is related to the distance from the earthquake and the material in which the earthquake is happening, as well as the nature of the movement of the earthquake, of the rupture. And the shaking intensities that we observed in February's earthquake, compared, for example, with the earthquake in September, were about 10 times as strong in certain locations. So for example, if we're looking at the information that was gathered here in the Heathcote Valley, these arrows here show the peak ground acceleration recorded at this station here. The blue arrow, the horizontal arrow, is the horizontal acceleration, and the red arrow is the vertical acceleration. And that vertical acceleration is about 2.2 g, and the horizontal acceleration is about 1.8 g. Contrasting that to September, in the Port Hills, we were looking at something around 0.25 g. So we're looking at about 10 times greater acceleration in the Heathcote Valley. And since the Port Hills are very, very close to the Heathcote Valley, one can assume that the peak ground accelerations experienced in the Port Hills is somewhere around that, somewhere within that magnitude. So we're talking very high ground accelerations. Once we've started looking at the accelerations, the magnitude of the earthquake, the shaking intensity, the next factor is the distance from the source of the energy. And again, going back to international case studies and information that people have been gathering for over 30 years, there are more or less some relationships defined, for example, by these lines, between the distance from the epicenter of the location you're concerned with and the magnitude of the earthquake. So for example, for a 6.3 earthquake, if you follow that line up, you would intersect these lines somewhere around the 25 to 30 kilometers. So one would expect that you would have some sort of land damage in a landslide point of view around within an area around 25 to 30 kilometers away from the epicenter. A different way of looking at this is looking at a particular case study. This is the Northridge earthquake in California in 1994. It had a 6.7 magnitude, and the location of the epicenter is here. And the line around this map shows the limit at which landslides were mapped in the surrounding area. And that limit is somewhere around 50 to 75 kilometers. So that's keeping in with that graph that I just showed, showing that there is a relationship between the distance and the occurrence of landslide type damage. So this is relating the distance to the magnitude. You can also relate the distance to the intensity of the shaking. So this graph shows, again from international case studies, the relationship between different types of magnitudes, so 7.0, 6.0, 5.0, each of them relating to a range approximately of shaking intensities. And looking at the horizontal graph, the horizontal portion of the graph, this is the distance away from the epicenter, and it's a log plot, so this is approximately 3 kilometers. That's why these lines are more or less horizontal. As you start getting away from the epicenter, the intensity of the shaking also goes down. And so that's very important, since the intensity of the shaking is one of the main triggers for the landslide to occur. So once we've looked at the magnitude and the intensity of shaking and realizing just how much shaking we had, what that peak ground acceleration was in that February earthquake, we know that we're going to have a lot of damage. And the way that that damage manifests itself depends on the material that's involved. We've got a couple of different classes of material in the Port Hills. The first one is the loess, which is the soil, the wind-blown silt that covers pretty much the top of all of the Port Hills. This material is quite unique. It has enough strength that it can stand vertically. If you can think back to driving through the Port Hills and looking at some of the cuts on the side of the road, and you see this sort of brown, vertical standing soil, that's the loess. It stands very happily vertically as long as it's dry. But this material doesn't have very much strength in the tensile direction, and so that's in a pulling direction. And once the shaking started, some of that material would, towards the edges of the faces, tended to want to pull away from some of the material further back into the slope. And that was creating some tensile stresses. And because the material is not very strong in that direction, it tended to break off. And so we had a few types of failures on some of the road cuts where actual blocks of loess came off of those cuts. That same tensile failure that we saw in the loess is also what leads to some of the fissuring, which David is going to talk more about in a moment. In addition to the loess, we have other types of soils, so some of the reworked soils due to erosion, some of the weathered soils due to the weathering of the rock that's there, the rock turning into a soil, as well as some of the really weak weathered rocks that sort of sit on the top. These materials are also susceptible to instability. They're susceptible to landslips. And during a seismic event, because we have the additional movement from the seismicity, these materials will have a tendency to slip even at very shallow angles. And finally, the Port Hills, for the most part, are made up of rock. And the rock in the Port Hills contains a lot of fractures in it. And especially the fractures that have very wide openings, where some of that material has moved away just through natural weathering processes. Those blocks that have moved away a little bit are very susceptible to seismic forces, which will tend to make them rattle and start coming off those slopes, those cliffs. And so this makes this material, because of its nature, it'll stand up vertically, so it creates these nice vertical slopes, like in this figure here. But because it's got the fractures in it, it'll tend to rattle itself apart and lead, as shown in this figure here, lead to some failure and rock falls that will end up either at the bottom or start rolling down the slopes. And this is the source material for the rock falls that we've had coming through some of the neighborhoods in the lower portions of the Port Hills. And then finally, adding on the aspect of topography, in order for us to have landslide type movements, we need some sort of topography. We need that material to be higher up. In addition to that simple need, different types of topography will lead to different types of failure. So the vertical cliffs that we end up developing in the Port Hills make them very susceptible to this rock fall and cliff collapse type of behavior because of the verticality. So this is an example from the Evans Pass Road showing multiple rock falls all along the road coming from this very steep subvertical cliff that's the source, and all along the Evans Pass Road there's rock falls. Similarly, this is another example of a sea-cut cliff. This is out in Scarborough at Whitewash Head. This is one of these sea-cut cliffs here that's more or less vertical or subvertical, and it was also susceptible to this type of failure. And this is some of the more dramatic failure, similarly to the Red Cliffs failure that we saw. And this picture demonstrates very nicely how this failure manifests itself within the cliff. Here, the tension cracks are visible through the grass and through the path. And these are far away from the cliff. And what's interesting about this is a picture taken February 23rd. Those cracks no longer exist because June 13th, this entire chunk of material here fell down during the earthquake. And we'll show a picture later of what this area looks like now. And so this is a demonstration of some of the dramatic failure that we see on these very vertical fractured rock cliffs. And the last aspect of topography comes from its nature as it tends to form peaks. This figure here shows a sort of a 3D image of a ridge. And there were seismometers and accelerometers placed along the ridge and along the bottom of the ridge to measure seismic activity from earthquakes, even from very far away. The graph demonstrates the amount of amplification of the peak ground acceleration recorded at each of these stations. And RH1 on the very left is a station located on the flank, so lower down towards the flatlands. And RH2 through 6 are all locations moving higher and higher up the ridge. And as you go higher and higher up the ridge, the amplification of those peak ground accelerations increases to almost 6 times what those accelerations would have been on the flatland. And so just the fact that we have this topography will tend to amplify what are also already large intensities of shaking. Taking all of this together, we've got the information from the nature of the earthquake that we've had, so some of the explanations about the amplitudes and the shaking intensities that we've seen, especially comparing the post-February events that we've had in comparison with the September event that we've had. Combining those with the distance, so this is a good example showing the distance of the September event compared to the distance of the February and the June events with respect to the Port Hills, which are located right about here. So putting the magnitude, the shaking intensity with the distance together leads to some of the very extreme and severe behavior that we've seen in the Port Hills, combining that with the nature of the materials and the topography to create the different types of failure mechanisms that we've seen in the different types of behaviors. And so keeping that framework in mind, I'm going to pass it over to David, and he's going to talk about a couple of specific examples and different specific types of behaviors that we're particularly concerned with, and that should be very interesting for you to learn more about.
Well, we'll follow on from that very useful presentation, because what I hope Marlene has done is given you a very clear understanding of the factors that have been involved in what we've seen over the past 6 months or so. I have to tell you that what we have seen, I believe, is something that was not expected by any of us from a technical or a geotechnical point of view, and we have not been embarrassed, but we have certainly had our eyes opened to what nature can achieve. The fact that we've been dealing with accelerations around twice that of gravity have made things that we have been accepting for granted for a long time turned on their head. It's been a very, very salutary experience for those of us who've been closely involved with this exercise. And of course, one of the things that we've been doing as part of this has been working very closely with the community as well as with the technical profession, the geotechnical profession, and understanding some of the really severe social trauma that has resulted from these events. And I don't want to dwell on that aspect because this is a technical presentation, but there is an aspect to it that I really want you all to appreciate and understand, because for me it has been a really interesting but challenging and difficult time, and it continues. As you're probably aware, the Port Hills have gone up by about 1/2 metre relative to the flatland. We have the Port Hills Fault. This is a plot from GNS, and what it shows as the change, the blue contours are the changes in the Port Hills. We don't believe we have a surface rupture, but we certainly have significant changes in terms of what's happened on the Port Hills versus what's happened on the flat land. And I don't need to point out any of those details because it's very obvious what is happening in that particular one. Notice that the major part of the change that we see is occurring around the eastern or northeastern part of the hills. And that's where we've seen greatest damage. One of the things that really struck me on the 23rd of February was to be able to drive straight over Dyers Pass. There were probably 2, maybe 3 boulders on Dyers Pass Road, but we couldn't get along the Summit Road, we couldn't go to many places, and that in itself started to tell us the severity of the problems. The Littleton Tunnel was closed, Evans Pass Road was impassable, all of these things were happening, and they made such a huge difference to the city that people were endeavouring to bring back to normality after September, where liquefaction was the primary issue. This was a whole new set of parameters, and ones that still are challenging and, I would suggest, troubling in their own respect. The points that I want to cover in terms of land damage are really 3. I'm going to go back and link with lateral spreading, which you've talked about already in relation to the liquefaction story. The second point I want to address is that the fissuring in Lurs is very, very similar to what we've seen in terms of the lateral spreading. And so I'm going to draw an analogy there, and I'm going to take you from the valley floor to the ridge crest. So we're going to work this in such a way that you start at the bottom with the liquefaction that many of you will be familiar with, maybe even from where you've lived, and then we'll work our way up the hill. Conventional rockfall and rock roll. These are problems that we've always had, we've always known about on the Port Hills. We've designed fences, we've designed ditches, bunds, various things to catch boulders that might come down occasionally. I recall back in, I can't remember if it was 92 or 94, we had a 50 cubic metre failure at the head of Raikura Place, and that was regarded as very large. We'll see Raikura Place in a later photograph, and you can't even see the head of Raikura Place anymore. So there are huge changes which have occurred. We considered boulder roll and rockfall to be not a trivial issue because of the velocity. They can't ever be regarded as trivial. But what they did was cause only isolated damage. That has now changed. We have to think again what Mother Nature is telling us. The third thing that I want to cover is the question of cliff collapse. And that's even more severe, because building a house on a rock is no longer the option, not when you're dealing with 2G acceleration. You just cannot consider that anymore. And if you want to live at the edge of the cliff with an excellent view, then you may not have it for long. So these are the realities, the new normal, as some people have expressed it. Things have changed. And there's that change that I want to emphasise to you tonight, because I've seen it now for 6 months, I've lived it for 6 months, and it's been a very salutary experience, I can assure you. So the land damage and the new Christchurch landscape are really what I want to emphasise now in the next 20 or so minutes. There's your lateral spreading. There were some photographs taken in September the 4th, and they show quite clearly movement towards water bodies. We've seen damage. We saw damage in places like Porritt Park to the rowing facilities. We saw major changes then because of the liquefaction and the lateral movement of riverbanks. So that's where we start. That's something that we've already seen. But now we want to go out to the valley floors, go up a little bit, not very far, have to go a few metres, even tens of metres, and we see something quite different. Now this particular diagram, those orange stripes are picking up the fissuring, what we're calling fissuring in the ground. And these fractures in the ground are the result of shaking damage. We see them in every valley from Bowen Vale out through Bridle Path Road. That's Bridle Path Road that you can see in the photograph there. Every one of these valleys is displaying this major fissuring. If you take the scale and work it out, that's about 800 metres along the valley side. Linear features. They were interpreted by some early on as indicating major landslides. EQC have investigated them, or some of them, as though they were landslides. But the reality is that this is fissuring, and Marlene addressed that by describing the low tensile strength of the loess. That's what we had, and that's what's caused us grief. The depth of these fissures, 5 metres, 6 metres, occasionally 7 metres, and that in itself causes its own set of problems. The causes of fissuring, try not to spend too long on this one, but they're elongate fractures, and those elongate fractures are in the loess soils. Drilling in Vernon Terrace has discovered 46 metres of loess down to bedrock. Far more than we ever thought. The maximum depth of loess we ever thought existed on the Port Hills was 20 metres, and we're now looking at double that figure. So we're learning an awful lot about what's going on. The length of these fissures, anywhere from 50 metres to over 500 metres, and I mentioned 800 in relation to Bridle Path Road. So these are huge changes. We get scarp development. There's obviously been a lateral movement component. So we have up to 300 millimetres, only that much, but it's enough. Sideways movement, and often part of the outside, the downhill part, will drop. And it may drop up to 300 millimetres. So it presents what appears to be the head scarp of a landslide. But these are long linear features and they keep on going. And they don't really curve out and generate major landslide failures. They taper with depth, these fissures, and they resemble what we call toppling. Toppling is a tipping over movement. And we find toppling in rock faces, we find them in quarries, we find toppling in loess. And these blocks that Marlene referred to coming off the faces are toppling failures, sideways, unconstrained movement of the blocks. There's no evidence been found yet for basal shears, as we would expect with a landslide, so we are looking at brittle failure of materials, tensile failure in a brittle material. And that produces its own set of issues. And so I'm just going to spend a couple of minutes talking about this particular feature because it's one that I'm pretty well familiar with. I've worked on LERS now for 30 plus years, longer than I care to remember probably, and it's not anything we've ever seen before, not anything I've ever seen before, I can assure you. This is a house site, doesn't really matter where it is, it's in Hillsborough Valley on the western side of St Martin's, near St Martin's School. The black lines that you can see quite clearly are the traces of the fissures, and they're below the house. The terrace on the left-hand side of the photograph, if you look at it, is uphill, and those fissures fortunately missed that house. However, if we go up here, up to number 1, those fissures go right under the centre of the house and the thing is completely broken. That house will not be reoccupied because of the effects of this fissuring. So it is serious, it's not life-threatening in the sense that it's not going to collapse the house, but it does cause problems. And the foundations are gone, they're shot, and therefore you cannot reoccupy that particular house. Now in the case of the house at number 3, that's gone in front of the house, it's missed it. There are tunnel gullies in the LERS, they're predating September, they've probably been there for a decade or maybe longer, and they're from stormwater not being controlled properly. But what we have done here at this particular site is have a little bit of a look at the problem, and we even took about half a dozen students out one Saturday and filled the fissures with LERS. That's what they look like on the ground. You can see there the cracks, they don't look much. You get too excited, you might drop an ankle in, that's probably about all you would do. But this is offset down slope. It's not a straight line, as you could see with those black traces before. And in this case, I've said here the feature was traced for 300 metres. We've now traced it for over 400 metres. So we know that it's a large feature and it continues. And again, there is no evidence for basal shear, but what it's done is create a set of problems. It broke a stormwater pipe. There's the stormwater pipe, and it broke as a result of this fissuring, and it was pouring water in there. It's caused the big erosion cavity that you can see. It's 1 metre deep, 1 metre wide, both directions. So, a bit of a problem. Where did the water go? We've got a fissure that we filled in here. There it is there. And so clearly the water has escaped. And what has been done in the last couple of weeks for this particular one is to dig it out, put in lime stabilised soil at the base, and then a mixture of bentonite and gravel, bring it back up, haunch the pipe and concrete over the cavity, and start all over again. And hope we don't have the same fissuring event next time, assuming there is a next time. So it's created its own set of problems. The fissures that we've seen extend deep down, but they tend to taper with depth. They're wider at the surface and narrower at the base. Again, in this particular excavation that you're looking at, we had a stormwater pipe going across, and it got broken and offset. It was actually a council stormwater pipe, and that in turn created its own set of problems until it could be fixed. If you live on the lower part of the hills, you may well be using flexible piping these days, because that's a safe way of making sure that we continue to pick up the water on the top side, deliver it to the downhill side, and don't have leakage getting into the soil and causing problems. So there are a number of practical issues that are part of this. But what we did was use bentonite. Bentonite's available from Colgate. Bentonite is a swelling clay produced by volcanic ash falling probably into a freshwater lake, and as a result it's converted into clay which is a very high swelling variety. So what we've had here is a mixture of 6 parts of what's called SAP 20, which is stabilised all passing 20 millimetre gravel, mixing it with bentonite in one part, and then placing that into the fissures. The good residents of Vernon Terrace, which is on the other side from Glenview, other side of the valley, wanted to do something to protect their properties quite early on. This would have been in April. And so they said, what can we do? So we said, right, we can fill these fissures with loess material and with bentonite. So we organised truckloads of bentonite and loess material, gravel materials, and they then had a working bee all one Saturday and did a 500 metre long fissure and filled it in. And that material then swelled and has largely, but not completely, alleviated the problem. So there are solutions, and it was very pleasing and encouraging to be able to work with a group of residents to give them some technical advice. It was done in a fairly simple way, I can assure you, but they were able to help themselves. And that's one of the positives coming out of something like this major earthquake, because the 22nd of February changed my thinking about the Port Hills and about what is possible and what is not possible. So, conventional rock falls. The boulder that you can see there with the person standing in front of it is the one that went through the house in Rapaki. And Marlene talked about the source area. The source area is up there, that part of the slope. It went through the front, out the back, and carried on. The cliff failure we'll come back to in a few minutes. I just want to talk briefly about conventional boulder roll. Now, what has been done as a method of analysis, and this is where we've been guided by Geological Nuclear Sciences, GNS, the approach that's been used has been to monitor what is happening in the various sites. You can see quite clearly there, I think, the steeper part of the slope, and what that is doing is giving us the source. That's where we're getting the material from. And then we define an angle from there. That angle there is called the shadow angle, and it's the angle from the horizontal down to the maximum extent of the boulder on the valley floor out here. That's 21 degrees. All of the analysis that's been done on the Port Hills gives us a magical angle of 21 degrees. That means that if you have houses within that 21 degree shadow angle, then you have the potential for boulders from that steeper face to actually hit them. Doesn't mean they will, but it does mean that there is a potential for that to happen. The other thing that you have over here, these are the mapped positions of boulders, the black dots in here, and you notice that the way it's set up is that you have the angle increasing, or the zone of impact, potential impact increasing as you go away from the source. What that tells you is that these boulders will bounce and they'll take different directions. They won't just go straight down the hill. They might bounce, go sideways, and we've erected a rule of thumb 30-degree cone either side to allow us to capture where we think the boulders are going to go. And so we address that as a generic approach, and then we have to go and look specifically at what's going on. Now, this is the worst one in Littleton. That's the source area. There's about a 5,000 cubic metre block of rock still perched up there. Only part of it's come down, but a lot of it has come down, and you can see it in the gully in the foreground, individual blocks in there. You can see blocks on the slope. That one's about 3 metres high. So we have some fairly interesting issues. In mapping them, what we've done here is pick up that source that I pointed out. There it is there. There's the source area. And then this is the cone that picks up where the boulders have gone and the area potentially impacted. So here we have all of these yellow dots down here showing us where boulders have ended up. That one on the left went through the back wall of a house. This one is another house in here which hasn't been hit, but it's at risk in this particular analysis. We've got another source area over here. Boulders down here, there's a house there. We're immediately seeing the sort of risk that exists, and we see that we have to deal with this and do something about it. That's looking back from that big boulder back down the valley. That's Littleton down below. The gully in the middle distance down there is the one that's captured most of these blocks. And those rocks have ended up in here. They've wrecked the road there. They've made a mess of it. And this is the house that was just beyond the immediate area of impact. So that's just outside, probably about 50 metres or so from the site. We now have to work out how to deal with this. We haven't actually remedied this one. We're remedying other sites at the moment, but not this particular one yet. It's in the too hard basket, only because it's going to be very costly. Probably looking at something like $1 million to remedy that particular problem. So these are things that we have to still deal with, and that's going to take some time. There are no simple answers. Prior to February 2011, rockfalls and boulder roll really were only considered, and we put in measures to catch boulders, ditches to collect them, and we used conventional trajectory analysis. There are various computer programs that you can get hold of. Rockfall is one of them, and that allows you to simulate 500 or 1,000 boulders falling off, and you can see where they end up when they hit the ground and how far they bounce and roll beyond that site. On the 22nd of February, something happened. We had much larger scale failures. We had cliff collapse. And it's the cliff collapse that is the next issue and the one that I want to finish up on. Whitewash Head. Marlene showed you the photograph before. There's the bit that she had in her photo. That's the bit now gone. You can no longer walk along that path. That's the walkway to Taylor's Mistake. I wouldn't take it. Many of these houses along here, they're $1 million plus properties, will not be reoccupied. The risk is too high. So, bear that in mind. Clifton Hill, one of the more expensive parts of Christchurch. Kinsey Terrace is the first road back from the cliff edge. That's a cliff face that we used to take our first year students to have a look at, and they would map it and they'd look at the face and they'd observe half a dozen lava flows, and we talked about lava flows following gullies and things of this sort. So this was quite a very instructive area. The sea stacks at the bottom of the cliff were obvious. Wave action had cut that cliff out, and that had been like that for 6,500 years since sea level reached its present elevation at the end of the last glaciation. That was stable, as far as we were concerned. That was it. And then, of course, sand had been added, sand from the Waimak had been added, and the estuary had formed, and all those other things that had taken place as the shoreline prograded. But suddenly, on the 22nd of February, and then again, more importantly, on the 13th of June, we've had about 30 metres off that cliff. There'd been very little happening in 6,000 years, and then bang, 2 earthquakes, both magnitude 6.3, very shallow, near-surface events, and we've lost that much cliff. The row of containers in that photograph is now too high, stacked one on top of the other, and the question is, how much more can we fit in there? And that road in the foreground is the only access into Sumner. Evans Pass Road is closed, Summit Road is closed. We've actually looked at moving that road out another 20 metres onto the beach to allow for more material to come down. Those are the realities that we're facing right now. What the outcome is, I don't know. I can't tell you. If I knew what was happening tomorrow, then it'd be good. This is Raikura Place. It's where we had a 50 cubic metre rockfall way back in 92 or 94, I can't remember which. It's a little bit different now. Person living in a house, the end of Raikura Place, was killed by the cliff collapse. That house there, about early 2011, I did a rockfall fence design for that house. The owner was concerned about getting the loose rock on the cliff face, and we did a conventional analysis and we decided a 3 metre high fence would do. Sorry, that house will not be reoccupied. Things have changed. I want you to go away with the understanding that things have changed dramatically. The Redcliffe School is having some problems. They've got some very nice coloured containers there protecting them. School hall here can't be used. They're likely to move the school across Main Road and closer to the estuary. There's some vacant land there that is looking very promising. And they'll increase the tsunami risk. But that's another story. Of the RSA in Sumner, we have some fairly interesting things. That's the RSA building down here, where somebody was also killed. I actually did the rockfall design for that house there, a long time ago. Richmond Hill Road, and hope you haven't got property in Richmond Hill Road, because these houses on the outside are in danger of being gobbled up by these cracks here. They're continuing right up, hundreds of metres up the road. There are a number of properties there that are not in a fit state, and they're not going to be there indefinitely. It is likely that a decision will be made soon for all of the houses on the, the western side, I guess, of Wakefield Avenue to be removed from residential use. Not that anybody's living in them now, they can't. But that's the reality. The top of Richmond Hill Road, with a hairpin bend in here, houses on the outside are likely to go. These are the new normal, the new reality that we're faced with. Brittle materials subjected to high vertical accelerations respond by developing subvertical fractures or fissures. We've seen it in loess, we've seen it now in rock. Around cliff edges, stresses at the free faces cause spalling. Blocks come off. This isn't a simple rock fall issue, this is a cliff collapse issue, quite a different thing. In the foot slope positions, the weak valley floor sediment still can displace locally, laterally, sideways, and that results in fissuring. We knew the young sediments of the Avon River were susceptible to liquefaction. We knew that 30 years ago. We mightn't have done enough about it, but we knew it. No one that I've spoken to has predicted fissuring in loess soils or fissuring in rock. We didn't know it was going to happen. That's the reality. The seismic sensitivity of the urban Christchurch area has been neglected at considerable cost. It doesn't matter whether it's 25 or $30 billion. It's by far the largest natural disaster in New Zealand history. And I think we just need to remind ourselves of that every so often. We're part of something far, far bigger than we have ever thought possible. So just remember that, please. How much did we really know geotechnically? Not nearly enough. But then would we have done anything differently? I'm not sure. So we were caught out by the close proximity and the shallow depth of faulting and with the 2G accelerations, because that's not something in the textbook. The codes are looking at 0.5G, maybe a little bit more, depending on the circumstance. Not 4 times that figure. And we certainly looked at cliffs which had sea stacks at their base, and we said, that's fine, that's stable. They weren't. They've fallen down. So what's the prognosis for Christchurch? Well, I guess the one that really says it all is shag pile. Remediation or protection of cliff top and cliff base properties may not always be possible. Well, I've just told you it's not. Not going to be. We're going to lose probably 100 houses, maybe more. Not the 5,000 due to liquefaction, but at least 100. Abandonment of sites could be the outcome, will in some situations be the outcome. The landscape of the city and of the Port Hills has changed forever. Things are now different. Accept that. And we have to move forward. And we have to learn from what's happened in the last 6 months. The end of September, or after the September earthquake, one of my colleagues prepared a report for the City Council. On the morning of the 22nd of February, he was about to deliver that report to the City Council. And it said, we've got everything sorted in terms of rockfalls. He had to tear it up and throw it away. That's the normality now. We got it wrong. On that note, I think that'll do, and right on the dot of 8 o'clock. There we are. Thank you.